Hi guys, and welcome to Module 9 review, where we talked about exponents, prime factorization, and order of operations. In this slide, we talk about exponents, and they're asking us to write each product as a power. So if we have 4 times 4 times 4 times 4 times 4, the base is 4, and that means that that's the number that we're going to multiply 5 times. And so the exponent here is 5. In this slide, we are asked to find the value of each power. And so if we have 7 squared, or 7 to the second power, that means we're going to take 7 and multiply it by 7, giving us 49. We talked about this important note in class, finding the value of a power when the exponent is 0. So the property of 0 as an exponent states that any number raised to the power of 0 is equal to 1. Let's go ahead and review some of these. We'll do the 10 to the 4th power first. 10 to the 4th power really means 10 times 10 times 10 times 10. And we talked about how easy it is to multiply with zeros. We're going to go ahead and multiply 1 all the way across. 1 times 1 is always 1, and now we can add all these zeros. There are 1, 2, 3, 4 zeros. And so our answer here is 10,000. Also, an important note is that if you have 10 to any power, the exponent tells you how many zeros there are going to be. Let's try 4/10 to the 3rd power. Let's try this one. And that really means that we're taking 4/10 times 4/10 times 4/10. And when we multiply decimals, we remember that we disregard the decimal and we take care of him at the end. So 4 times 4 is 16, times 4 is 64, and now we can worry about that decimal point. So we're going to move it over 1, 2, 3 times. So we go 1, 2, 3, and so the answer here is going to be 64 thousandths. The next one that we have is 3/5 to the 0 power, and the property of 0 as an exponent states that any number to the 0 power is equal to 1. So it doesn't matter if it's a fraction, a decimal, if it's a whole number. Anything to the 0 power is going to be equal to 1. And the last one that we're going to do is 2/3 squared. That means we're going to take this fraction and multiply 2/3 times 2/3. And when we multiply fractions, we just multiply straight across. So 2 times 2 is 4, 3 times 3 is 9, and so the answer here is 4/9. When we find the square of a whole number, that makes it a perfect square. So let's talk about identifying those perfect squares. They tell us that 64 is a perfect square because if I take the base number 8 and I square it, or I multiply it by itself, I get 64. Now 20 is not a perfect square because there is no base number that I can square or multiply by itself to get 20. I'll prove it. Let's start with 4 squared, for example. 4 squared equals 4 times 4, which is 16. Well, that's not 20. So let's try 5 squared. 5 squared means 5 times 5, and that equals 25. And so we know that there is no base number that we can square that'll get me to 20. Therefore, 20 is not a perfect square. In determining whether these numbers are perfect squares, we're thinking about putting a base number that when we square all of these, we will get that number. So let's try 25. I know that if I do 5 squared, I do get 25, and so yes, 25 is a perfect square. Now 2 is not a perfect square because if I do 1 squared, 1 times 1 is 1. If I do 2 squared, 2 times 2 is 4, and so 2 is not a perfect square. Let's try 99. Let me think of a factor that'll get me close to 99. Let's do 8 squared, which is 64. 9 squared is 9 times 9, which is 81. 10 squared is 10 times 10, which is 100. So 99 is not a perfect square. And we pretty much answered this next one. 10 squared is 10 times 10, which is 100, and so 100 is a perfect square. In class, we talked about the importance of knowing the divisibility rules, and there is a wonderful poster in our classroom. For the purposes of this lesson, we talked about just the more common divisibility rules. So we're going to talk about the divisibility rules of 2, 3, 5, and 10. The divisibility rule of 2 states that if the last digit is even, then we can always divide it by 2. So for example, anything that ends in 0, 2, 4, 6, 8 is divisible by 2. Divisibility rule of 3 says that the sum of the digits, if it's divisible by 3, then we can always divide it by 3. So let's think of an example where this is extremely beneficial. We talked about this in class, where if I told you, for example, to simplify 162 to 522. Now, this, if we didn't know the divisibility rule of 3, would be a difficult place to start. Well, we could divide by 2 because they're both even numbers, but we can divide also by 3 because the divisibility rule states that if we add these numbers, 1 plus 6 plus 2, and the sum or the total of them, this is 1 plus 6 is 7 plus 2 is 9. If that is a multiple of 3, then we can divide it by 3. The same with 5 plus 2 plus 2. Well, that's also equal to 9. And so I know that I can at least divide these by 3. The divisibility rule of 5 states that if the last digit ends in 5 or 0, then we can divide by 5. For example, numbers like 10, 15, 20, 25, 30, 35. Anything that ends in 0 or 5, you can divide by 5. And lastly, a number is divisible by 10 if it ends in 0. And that's very, very simple to think about, because what we do in class when we cancel out those zeros, that's really what we're doing. We're dividing by 10. In class, we talked about the difference between a prime and a composite number, and we put our hand underneath our chin and we said the word prime, and we noticed that we touched our chin only one time. Whereas when we said the word composite, we hit our hand multiple times. And this is a good way to remember that prime numbers only have one factor pair. It's that number times 1 only. It's the only way that we're going to reach that number. Whereas a composite number has more than one factor pair. So for example, 24 has 1 times 24, 2 times 12, 3 times 8, 4 times 6. We talked about prime factorization, and we talked about finding the prime factorization of a composite number. And what it is prime factorization ultimately means that our answer is going to be prime factors. So for example, they give us the example here of 60, and we started with the factor pair of 2 times 30. Now we went ahead and circled 2 because that is already a prime number, so he's going to be part of our product answer. And then our goal is to continue to break down these composite numbers until everything is prime. And so we still have 30, and to get 30, the factor pair would be 2 times 15, again circling the 2 because that is a prime number. So every time you hit a prime number, you would circle that because it's going to be part of our answer. 15 is also composite. We further break that down to 3 times 5, which are prime numbers. So the prime factorization of 60 would be those numbers that we circled, those prime numbers, 2 times 2 times 3 times 5. And we also talked about how now we're in 6th grade, so instead of saying 2 times 2 times 3 times 5, we would say that is 2 squared times 3 times 5. In class, we discussed that when we are writing the prime factorization of a number, we can choose any factor pair to begin the factor tree. So for example, we talked about how one student might feel more comfortable if you have to find the prime factorization of 48 to start with 2 times 24 and then further break that down. 24 is 2 times 12, and then 12 is 4 times 3, and finally 4 is 2 times 2. So the prime factorization of 48 would be 2 times 2 times 3 times 2 times 2, or 2 to the 4th power times 3. Now, we discussed how if another student wanted to try to begin with a different factor pair, such as 16 times 3, which is also equal to 48, they can do that. We further break down 16, 2 times 8. We further break down 8, which is 4 times 2. And lastly, break down 4, which is 2 times 2. Again, the prime factorization is 3 times 2 times 2 times 2 times 2, or 3 times 2 to the 4th. Now, the commutative property of multiplication states that if we multiply 2 to the 4th times 3, or 3 times 2 to the 4th, we still end up with the same answer. It's just like if you have 2 times 3 and then you just switch 3 times 2, you're always going to end up with 6. So it doesn't matter which factor pairs you begin with. What does matter is that we ultimately reach the same prime factorization. In this slide, we were reminded of the factor rainbow that we did. If in this example, Anna wants to build a rectangular garden with an area of 24 square feet. This is important information, 24 square feet. What are the possible whole number lengths and widths of the garden? So what we really want to think about is the factor pairs of 24. When we do our factor rainbows, we always start with 1 because that way we know that we're not going to forget any factors. So 1 times 24 will get me to 24. 2 times 12 will get me to 24. 3 times 8 will get me to 24. 4 times 6 will get me to 24. 5 times nothing will not. 6 will, but we're moving backwards, so we know we have all the factor pairs. So the factors of 24 are 1, 2, 3, 4, 6, 8, 12, 24. Now, most of you are familiar with and enjoyed the factor tree with the prime factorization, but you can also use a ladder diagram in order to reach those prime factorizations. So the way the ladder diagram worked is they start us off with the number 36. So this is the one that we're trying to find the prime factorization for. And the number 3 was given. So really what they're doing is dividing 36 divided by 3, and that gets us 12. So, and all the composite numbers go inside the step, and all the prime numbers go outside the step. So when we did 36 divided by 3, we ended up with 12. And now we're thinking of a prime number that we can put outside that we can divide 12 by. So you can use 2, you can use 3. Let's go ahead and stick with 3. And so again, the composite numbers go inside the steps where the prime numbers go outside. So 12 divided by 3 gets us 4. And I'm thinking of a prime number that I can divide 4 by to get a whole number. So 4 divided by 2, and that will get me to 2. Now, if you notice, the ladder diagram always ends with a quotient of 1. So we need to think about what number, when I divide by 2, will give me 1, and the answer is 2. So all the numbers outside of this ladder diagram are your prime numbers, which means this is your prime factorization. So 3 times 3 times 2 times 2. And let's go ahead and make sure that that does get us to 36. So 3 times 3 times 2 times 2. We're going to check that. So 3 times 3 is 9, times 2 is 18, times 2 is 36. So we know we have the prime factorization correct. The only other thing that I would suggest that we do is turn these into exponents. So 3 times 3 is the same as 3 squared, and 2 times 2 is the same as 2 squared. So our final answer is 3 squared times 2 squared is the prime factorization for 36. We discussed the importance of analyzing errors in class, and in this example we had someone that made the error of stating that 8 cubed, or 8 to the third power, was equal to 8 times 3. And you guys identified the error by stating the base number cannot be multiplied by the exponent. That's not going to get you to the correct answer. So you guys correctly stated that we would have to take the base number and multiply that 3 times. And so the correct answer would be 8 times 8 is 64 times 8. And so we go off to the side here and we go 64 times 8. 8 times 4 is 32. 8 times 6 is 48, plus 3 is 51. And so our answer is 512. We also revisited order of operations, and we talked about working the parentheses first and then exponents, multiply, divide, whatever comes first from left to right, and then add, subtract, whatever comes first from left to right. We talked about how you guys are very sure about always working what's in the parentheses first. We are going to see a lot more exponents now that we're in 6th grade. That goes next. When we get to the multiply, divide, remember, be careful. It's not necessarily always multiply first. If the division comes first, then you divide first. So it's whatever comes first from left to right. The same with add, subtract. And the only difference with the order of operations that we're talking about for this module is we discussed numerical expressions being expressions that contain only numbers and operations. So for example, something like 2 plus 3 is a numerical expression because it's filled with numbers and operations. So similarly, an expression like 7 times 9 is also a numerical expression because it's filled with just numbers and operational signs. So to evaluate these and to solve for them, we would have to follow the order of operations. So now that we have discussed rational numbers and negative integers in 6th grade, it's important that we understand that when we solve order of operations, our answer might potentially be a negative integer or it might be a rational number. So let's go ahead and work this first one. It's 2 plus 5 in parentheses minus 4 squared. The order of operations says work what's in the parentheses first. So 2 plus 5 is 7, and then I'm going to rewrite everything else. So 7 minus 4 squared. Order of operations says that now I have to do exponents next. So 7 minus 4 squared really means 4 times 4, which is 16. Now 7 minus 16, and we discussed this, if we look at this on a number line and we start at the number positive 7 and we take away 16, we're moving to the left on the number line. So we're going to end up at negative 9. Let's try this next one. Negative 4 plus 3 cubed divided by 5. Order of operations says do what's in parentheses first. There are none, so we move on to exponents. Remember, you rewrite everything else. So negative 4 plus 3 cubed really means 3 times 3 times 3. 3 times 3 is 9, times 3 is 27, divided by 5. Order of operations says we do multiply, divide, next, whatever comes first. So we do have a division here of 27 divided by 5. And again, you weren't exposed to these type of problems when you learned order of operations in 5th grade because you weren't exposed to rational numbers yet. Well, now in 6th grade, you know that you can take 27 divided by 5, and 5 goes into 27 5 whole times, and you're left with 2. Well, that's smaller than my divisor, so you know we're going to start introducing our decimal and zeros until we reach a terminating decimal. So 5 goes into 24 times, and so the answer here, 27 divided by 5, is 5 4/10. Well, we can't forget about what's left of our numerical expression. So negative 4 plus 5 and 4/10. What we have here is, if we were on a number line, we're at negative 4, and I'm telling you to add 5 whole and 4/10. That will leave you at 1 and 4/10. And if you really think about it, what this numerical expression is saying is 5 and 4/10, and then you're taking away 4. That's really what this is saying. So you're left with 1 and 4/10. So let's practice some. When given this numerical expression, 30 divided by 7 plus 2 cubed in parentheses times 6, looks pretty difficult, but if we follow the order of operations, we should be okay. Parentheses first, and so 2 cubed is really the same as 2 times 2 times 2, which is 8. So if I do what's in the parentheses first, that's 7 plus 8. And so I have 30 divided by 15 times 6. We take, this is a great example here when we reach this point that even though it's multiply, divide, it's whatever comes first from left to right. So we would not multiply first. Here we would divide 30 divided by 15, giving us 2 times 6, and the answer here is 12. Had you not followed the order of operations and you would have multiplied before you divided in this part right here, you would have ended up with a different answer and you would have been incorrect. We covered this type of example in class, and we talked about how important it is to follow the order of operations. In this example, we're given the numerical expression 21 plus 3 squared divided by 3. And so the only thing here that's being squared with the exponent is that numerator. So be careful with that. And so we have no parentheses. We go on to the exponent. So we rewrite the rest of the numerical expression. 21 plus 3 squared is the same as 3 times 3, which is 9, and then over 3. We understand that this fraction bar means divide. So it's multiply, divide, whatever comes next. So we divide 9 divided by 3, and that gives us 3. We rewrite the rest of the numerical expression, which is 21 plus 3, and the answer is 24. In this example, we start with the numerical expression 8 plus, the numerator is 12 minus 8, that's squared, divided by 2. So what's in the parentheses is what we're going to work first, and so we're going to go 12 minus 8, which is 4, and that's what we're going to square. So when we rewrite this, we will rewrite 8 plus, we have already determined that 12 minus 8 is 4. We're going to square that, divided by 2. Next in the order of operations is we're going to evaluate the exponent. So 4 squared, or 4 times 4, is 16. And we're going to go ahead and set that over 2. And we rewrite the rest of the numerical expression. So 8 plus 16 divided by 2. Divide goes next. 16 divided by 2 is 8. And 8 plus 8 is 16. This is a really interesting problem that we want to discuss. So in this example, John wants to simplify the numerical expression 5 plus 3 squared. And what he does is he rewrites 5 plus 3 squared as 5 squared plus 3 squared. Is he going to get the correct value for the expression? If not, what should he do to simplify the expression? Well, the order of operations tells us that we better work what's in the parentheses first. So 5 plus 3 would be 8 squared, and we know that that means 8 times 8, which is 64. What John did is he took the 5, squared that, and then added 3 squared. Well, 5 squared is 25, plus 3 squared is 9. So that's going to give us an answer of 34. And no, he is not going to get the correct value. And in this example, it's so very important that we note that if you do not work what's in the parentheses first, nor follow the order of operations, you will get an incorrect answer. I hope you enjoyed our review of Module 9. That wraps it up. If you have any questions, please feel free to ask.